Let's look at a second example today where we use the Clausius-Clapeyron equation to calculate a vapor pressure at a different temperature condition. So in this case, we're told that the vapor pressure of ethanol, which has chemical formula C2H5OH, is 100 millimeters of mercury at 34.6 degrees Celsius. The enthalpy of vaporization under standard state conditions, delta H naught VAP, is 38.6 kilojoules per mole. We want to know what the vapor pressure of ethanol, abbreviated capital P subscript ETOH, similar to the partial pressure of ethanol, is if the temperature increases to 65 degrees Celsius. So take a minute to visualize the situation. We have some ethanol sitting in a beaker. This would be the simplest version of this experimental condition. We have some ethanol sitting in a beaker. It's in a hot room. The room temperature is 34.6 degrees Celsius. We make a measurement of the vapor pressure, which is related to the ethanol molecules vaporizing and entering the gas phase above the liquid layer in the beaker. So at 34.6 degrees Celsius, some of that ethanol is evaporating, and it's enough ethanol to generate a partial pressure of ethanol of 100 millimeters of mercury at that room temperature. Now we transfer that ethanol to a hot water bath where the temperature is 65 degrees Celsius. We'd like to know what the new vapor pressure above the liquid in the beaker is going to be. The only other piece of information that we're given and the only other piece of information that we need is the enthalpy of vaporization, delta H naught VAP. It's 38.6 kilojoules per mole. All right, so our strategy here, since we are given a vapor pressure and a temperature and the enthalpy of vaporization, and we're asked about the vapor pressure at a different temperature, this is a Clausius-Clapeyron equation. Now watch out, because these gas phase equations are starting to stack up, and in the next chapter, we're going to encounter even more of them. So you've got to start thinking in your brain, what tool do I use for which job? The Clausius-Clapeyron equation is for calculating the new vapor pressure of a liquid at a higher temperature. So if you have a vapor pressure and a temperature, and you have an enthalpy of vaporization, and you're asked about a new vapor pressure, that's a Clausius-Clapeyron equation job. We are going to use the Clausius-Clapeyron equation to find the partial pressure, the vapor pressure of ethanol at 65 degrees Celsius. We're ultimately going to need the temperature in Kelvin, not Celsius. So I'm going to go ahead and add 273.15 to my 65 degrees Celsius. My temperature in Kelvin is 338 K. That's how I'm going to have to use it in the equation. Really 338.2 K to force things. Now we solve the Clausius-Clapeyron equation for the higher vapor pressure P2. So our general form of the Clausius-Clapeyron equation is the natural log of the higher vapor pressure P2 is equal to the natural log of the lower vapor pressure P1 plus delta H naught over R times 1 over T1 minus 1 over T2, where T2 and P2 are the higher temperature, higher vapor pressure conditions. Okay, so a couple of modifications that I have to make on my original measurements in terms of getting them in the right units. My enthalpy of vaporization was given to me in kilojoules per mole, but when I put it in the Clausius-Clapeyron equation, it has to be in joules per mole. Your units have to work out and cancel. Because my gas constant is in joules per Kelvin per mole, my temperatures have to be in Kelvin. My enthalpy of vaporization has to be in joules per mole for these units to cancel out. So I have to take my delta H naught VAP that was given and convert it to joules per mole by multiplying by 1,000 joules in 1 kilojoule. My enthalpy of vaporization, as I'm going to use it, is actually 38,600 joules per mole. So now I have my measurements in the right units. We never have to worry about pressure units when we are talking about what are the units on the vapor pressure, because we're taking the logs of the vapor pressure measurements and that undoes the units, but you're always getting P2 back in the same original pressure units that P1 had. So if P1 is in millimeters of mercury, I'm going to get P2 back in millimeters of mercury as my units when I solve for P2. So here are my numbers going in. T1 is 307.9 Kelvin, that's 34.6 plus 273.15. T1 is 338.2. We already calculated that one, but my temperatures have to be in Kelvin here. I'm going to take the difference of these two and I'm going to multiply that by 38,600 divided by 8.315. Make sure you're using the 8.315 gas constant with the Clausius-Clapeyron equation. We have two versions of that gas constant now. You need the one that's in joules per Kelvin mole. The units matter when you're doing these types of calculations. If you use the other value of the gas constant, you're going to get a non-physical answer that doesn't mean anything. The algebra will be happy to sort itself out for you, but you won't get an answer that means anything. All right, natural log of 100 is 4.6052. My difference in the reciprocal temperatures here was 0.0002909. Inverse Kelvin would be the units on that. Times 4642.49. Units are Kelvin on that, so the units cancel out, and I can add these two numbers together. 4.6052 plus about 1.3 gives me the natural log of P2 is equal to 5.9561. To isolate P2 and undo this natural log, I raise each side over E. So I have E to the ln P2, the E and the ln cancel each other out, leaving me with P2. P2 is equal to E of the right-hand side, E to the 5.9561, which is equal to 386.1 millimeters of mercury. So we would predict that the vapor pressure at the higher temperature is 386.1 millimeters of mercury. So that's how we use the Clausius-Clapeyron equation. It may look like any other equation. You can just put numbers in and plug and chug. But between the unit conversions that you have to do and the use of E and ln in terms of solving the natural log equation is something that I see a lot of Gen Chem students have a problem with the first time around. So if you have questions about how the units sort themselves out, how to rearrange the algebra to solve for what you need most efficiently in the Clausius-Clapeyron equation, or just how to enter the syntax on your calculator, please don't hesitate to reach out and ask me, ask a friend, ask a tutor, but make sure you get that information and that you can use the Clausius-Clapeyron equation effectively when you need it.